Okay, so let's get started. Today's speaker is Agostino Marinelli from SLAC. In the last several years, SLAC has developed, has made big strides in synchrotron light, converting the LINAC in a free electron laser. Now we have the image. I have missing photons. There's so many X-ray photons that now the visible ones have gone. But anyway, so Agostino has been in the middle of various accelerator physics developments with the free electron laser up there. He actually, him and I share the university where we started, the University of Rome, at least the only University of Rome that there used to be. Now you have to specify better, but at least in my days there's only one of them. And then he had a PhD from UCLA, where there's lots of accelerator physics being done. He was then postdoc at SLAC, Panofsky's fellow at SLAC, and then since 3 years he's on the faculty up at SLAC. And so it's a pleasure to actually have this, so we are alternating topics. ZX came, I'm sure, wonderful talk last week. I was not here, so sorry I missed that. But now we're actually glad to have Agostino here. Thank you.
Thank you. Can you hear me?
Yes.
Oh, great. Okay. Yeah, thanks for inviting me. I normally only come here for teaching, so it's fun to meet more colleagues and more students beyond just my class. So I'll talk about attosecond science with X-ray free-electron laser. I'll try to give a little bit of an introduction on how FELs work, and then I'll show you what I'm personally excited about, which is just imaging in general, detecting the motion of electrons on their natural timescale. Before I get into the technical part of my talk, I'd like to acknowledge acknowledge everyone who works with me at SLAC. So we have a group of young students, young staff, and postdocs working on attosecond science, and it's led by myself and James Cry. And most of the work you'll see is done by this group of people. And I'll try to highlight the contribution from students. I really want to point out there's a lot of opportunities for students in this research area. And in general, this work is the fruit of very large collaborations. As you'll see, FELs are big machines, and the experiments are difficult, and so they typically involve large collaborations. Specifically, I'll show you the XLEAP and XLEAP2 results, which is essentially the project that led to the generation of attosecond pulses. And then this collaboration that's also led by myself and James, where we're actually trying to use these attosecond pulses for something interesting. And then in the last couple of slides, I'll show you what how we're trying to go beyond this paradigm of high gain FEL using plasma accelerators, and that's a collaboration that we have with the FACET facility and also a few different groups at UCLA. Okay, so this is a talk about X-ray science. So I'll start by introducing what X-rays are. So X-rays, there are a few, you can find different definitions in literature. Personally, I like the one from David Atwood that says that X-ray is anything above the carbon K edge at 280 electron volts. And the reason why that is will become clear soon. And you typically distinguish soft X-rays, which is mostly what I'll be talking about here, which is anything between the carbon K edge and well, it depends who you ask. In the context of my talk is up to 1 keV, and then anything in the few keV to tens of keV range is hard X-rays. And then this is, again, it's a talk about attosecond X-ray science. So what is an attosecond? It's 10 to the minus 18 seconds. Just to give you an idea of the scale, this is a standard, common thing to say about attosecond science. 1 attosecond is to 1 second, the same as what 1 second is to the age of the universe. It's really fast time scale. But more importantly, for science, the reason why attoseconds are important is because they are the time scale of electronic motion. So if you look at this hierarchy of time scales in molecules, you have molecular rotation that happen pretty slowly on picosecond scales, then you have molecular vibrations, and in general the rearrangement of the nuclei in a molecule. It happens in the scale of tens to hundreds of femtoseconds. And then the 1 femtosecond is really what separates the motion of nuclei and the motion of electrons. So electrons can move around, small molecules on the scale of hundreds of femtoseconds to a few, hundreds of attoseconds to a few femtoseconds. You can convince yourselves that that's the case just by looking at, this is just standard textbook quantum mechanics. If you have a superposition of excited states in a quantum system, then you'll have different eigenfunctions that evolve to each according to their own time frequency. And so the time scale of, say, the evolution of this superposition is typically h bar divided by the width of energies that your superposition of states is covering. And so then you want to throw in some numbers here. And I think a good number to look at is the 1 femtosecond. So a single femtosecond Gaussian pulse, so Fourier limited, has a full width of maximum bandwidth of roughly 2 electron volts. So if you compare these 2 electron volts with the typical excitation energies of valence electrons, then you convince yourself that those are typical in the few electron volt range. So if you have a superposition of them, you can imagine observables can evolve on time scales of hundreds of attoseconds to few femtoseconds. And then, of course, you can go even faster if you look at core electrons. Personally, I don't find those particularly interesting. I think the ones that are really interesting are the valence electrons, because, of course, they're the ones that drive chemistry. Now, so attosecond and X-ray vision are actually known in, say, popular culture as superpowers of some of our superheroes. And namely, the Flash has attosecond vision and Superman has X-ray vision. And I was really hoping I could find some really inspiring quote or some way. I was hoping I could say something inspiring about how we are, reproducing the superpowers of these two superheroes. But I actually scavenged the internet and I found that these two actually made a pretty lousy use of their gift. The Flash is not too bad. He says if you have attosecond vision, you can see everything and everyone. Maybe it's a little creepy and ethically questionable, but at least it's compelling. Superman instead is pretty bad. He claims that he can see through walls thanks to X-ray vision. You can only do that if people inside beyond the wall are emitting X-rays, or if you're blasting them with enough X-rays to detect backscattered X-rays through a wall. So either way, they're all dead at the end of the measurement. So then that doesn't work, and he engages in some pretty irresponsible behavior. I've looked at what else does Superman do with his X-rays? Well, he boils the ocean for some reason, or he sets these old man's savings on fire. I don't know. Not exactly the world's finest. So where am I going with this? There is a much better way to use X-rays. So as a society, we have acquired X-ray vision, and we make much better use of it. So X-ray science is a collection of very many different techniques, but you can more or less divide X-ray techniques in two groups. One is X-ray imaging, and the idea is that in any imaging experiment, the smallest thing you can see is on the order of 1 wavelength. And so since X-rays have wavelengths of nanometers to angstroms, then that tells you that here you can achieve spatial resolution on the scale of the size of an atom, right? The size of an atom is roughly one angstrom. And then the other set of techniques, completely different, but achieve similar goals, is X-ray spectroscopy. The idea here is that X-rays you can tune X-rays to the absorption, to the energy levels of core electrons in atoms. And it just so happens that these energy levels are very widely separated from each other by hundreds or tens to hundreds of EVs. So that means that now if you tune your X-rays to some specific absorption edge that corresponds to one element, you can look at a somewhat complicated molecule and get information that is localized to the specific atomic site you care about. So either way, with X-rays, you get information about your sample at the atomic level. So then why would you care about attosecond and X-rays? Well, I've told you that attosecond, say hundreds of attoseconds to few femtosecond timescales are the typical timescales of valence electronic motion. And so now if you have attosecond, if you can access attosecond and X-ray information, then you can follow the dynamics of valence electrons, but in a localized way, right? So this is an aminophenol molecule. You'll see this a lot because it's actually the sample of one of our experiments. And our collaborators in Madrid, they've done this simulation where we impulsively remove one valence electron from this molecule with a very short pulse. And then we look at what happens. This is the hole and charge density across the molecule. And what happens is that now this charge density is moving around the molecule on the time scales that I've told you about. So in fractions of a femtosecond. And the idea is that now if we can excite this motion and then probe this molecule with soft X-ray pulses, then we can access localized information. So if we care about this oxygen atom here, we'll tune our X-rays around the oxygen edge. If you care about these carbon atoms here, you'll tune your X-rays close to the carbon K edge. And if you care about this nitrogen atom here, you'll work around 400 dBs. Okay. So why is this important? Well, I've told you, it is attosecond science is the study of electron dynamics, and the reason we should care, there are several reasons. Are there any chemists here? Anyone who identifies as a chemist? No, great. So this is a statement that if you're in a room with chemists, you have to put a lot of qualifiers before this statement. But it is the first step in chemistry. It typically involves the motion of valence electrons. The reason why I say that in these qualifiers is because it's still unclear whether there is it's still unclear how much the coherent electronic motion actually affects chemistry. But it is from a temporal, on the temporal scales, it is the first thing that happens. Of course, electron dynamics, they're the first step in radiation-matter interaction, which of course is the basic ingredients of a lot of things we care about, like photosynthesis and solar energy. In general, it's a test of multi-body quantum mechanics. It's a really good way to test these quantum chemistry codes that can solve the Schrödinger equation for relatively large molecules. Now, this is a field where there is a lot of variety of opinions. Typically, you ask 10 people the same question, you get 11 different answers about whether something is interesting or not. So I'm throwing my opinion out there, and the reason why I think this is interesting, or at least the reason why I think we should be spending millions of dollars on these experiments, is that the Schrödinger equation for a molecule cannot be solved numerically, even if you have thousands of nodes on a running your simulation code. Anything more complicated, say, than a hydrogen molecule or a helium atom, you can't solve the Schrödinger equation numerically. And so the reason why I think we should be spending all this money doing these experiments is so we can create data to come up with better models to simulate molecular systems theoretically. Okay. So a little before I get into the technical part of my talk, I want to maybe have a little summary of what I just said. One is that electron dynamics in molecules is poorly understood, and it is an interesting problem. And we need attosecond time resolution and atomic size specificity if we really want to understand it. Right? So what it really means is that we need intense attosecond X-ray pulses. That's what's going to give us the experimental infrastructure to understand this problem. So where do we of course, what will give us these attosecond pulses? It's said in the title of my talk. It's X-ray free-electron laser. What is an X-ray free-electron laser? It's easier to say what it does than to say what it is. It's the source. It's the brightest source of X-rays available. You can compare. This is the peak brightness, which is essentially the number of photons per unit phase space volume, so per unit time, frequency, solid angle, and area. And it is about 10 orders of magnitude brighter for X-ray free-electron laser than for synchrotron radiation sources. In the context of this talk, it's actually more interesting to compare FELs to high harmonic in gas sources, because that's the only other light source that can give you attosecond pulses. Even in this case, the free electron lasers do very well compared to the alternative. What you see here is the pulse energy as a function of photon energy. These are different data sets. These are all taken using high harmonics in gas. This is a tabletop technique. You have a laser, you shine it on a gas jet, you get high frequency radiation on the other side. And there's a pretty clear trend here that as you go to higher and higher photon energies, your flux decreases dramatically. So here in the soft X-rays, you're looking at picojoules per pulse, which is not great, if you're trying to do things like pump probe experiments that I'll talk about later. But if you work with a free electron laser, then you're up here in the tens of microjoules. So there's a huge gain going from tabletop sources to FELs. Not only that, but also the threshold for nonlinear interactions, which, as I'll talk about later, it's also the threshold where you can actually do pump probe experiments. And any pump probe experiment is inherently a nonlinear experiment. And we're well above that threshold. So we are in a regime where we can make good use of these attosecond pulses. I will say recently we have actually gone even higher in pulse energy. This is the work of Paris France. She's an applied physics graduate student. So we're looking now at hundreds of microjoules and terawatt, order 1 terawatt peak power. So again, huge gain and also enough intensity to do useful things. And I know when we talk about free electron lasers, one is always tempted to say that free electron lasers are expensive. But if you look at the cost per photon, actually they're a lot cheaper than tabletop sources. And a FEL will cost you about $1 billion, and a tabletop HHG source will cost about $1 million. So it's about a factor of 1,000 cheaper, but you get 1 million times more photons with the FEL. So, you get more than what you pay for. All right. So this looks pretty promising. It looks like FELs, we're on a good track to do useful attosecond science. How does a free electron laser work? What are the ingredients first? You need an electron beam that's very bright and an energy of 4 to 20 giga-electron volts. So with current technology, this is a pretty sizable accelerator. It's about 1 kilometer. And then you need a long undulator. An undulator is exactly what the name sounds like. It's an array of magnetic dipoles. It's a periodic array of magnetic dipoles. So what it does is it makes electrons wiggle and they emit radiation. So that's, you'll find undulators also in synchrotron radiation sources, but what's special about the free electron laser is that you get microbunching. So if you have a single electron going through an undulator, what the single electron does is it emits a wavelength that is essentially the Doppler shifted replica of the undulator wavelength. So this is typically a period of centimeters, multiplied by 1 over gamma square, you get X-rays. And this is, like I said, this is true of any X-ray source based on relativistic electrons. What's special about the free electron laser is that you can actually get a huge increase in peak power thanks to microbunching. So what happens is you have a collective instability. Your beam starts as essentially a random distribution of electrons. And the interaction between the electrons and the X-rays causes the electrons to microbunch. And at the end of the undulator, what you have is your electrons are distributed in small packets. They are 1 wavelength away from each other. And what happens is that now all the radiation that they emit is emitted in phase. And so you get a large gain of order 10 millions going from this incoherent radiation to the coherent radiation. And of course, this happens over the length of the undulator. There's this very famous video from Sven Reiche that shows this is the distribution in Y and Z in one slice of in a few slices of the electron bunch. And you see it slowly creates microbunching. So typically, this is the point where you have the most power, and then the microbunching is destroyed as the particles get past each other. All right, so that's the FEL instability. This is what it looks like in real life. You can go to LCLS. This is taken from the first lasing paper 12 years ago now. I wasn't at SLAC. I'm not taking any credit for this. But you can go to the control room at SLAC and do this measurement whenever you want, and you'll get more or less a similar answer. Well, you can measure the pulse energy or the power as a function of the position along your undulator. Your undulator is about 100 meters long, and what you'll see is that you have this exponential growth, and you start from the spontaneous level, and you get up to the saturation power, which is orders of magnitude higher than what you started from. All right, so this is what the FELs look like. Like I said, they're pretty sizable devices, not something you can put in your basement. The joke is if you want a tabletop free-electron laser, you have to build a really long table. So this is what it looks like. A SLAC, we have 3 kilometers, a 3 kilometer tunnel. The third kilometer is what we call LCLS, which is the free-electron laser that's been working for the last 12 years. And now in the first kilometer, we have LCLS2, which is really exciting. It's a superconducting accelerator. So what that does is instead of shooting 100 times per second, like LCLS, it shoots 1,000,000 times per second. So, you can imagine, more data means you're able to see smaller, more rare events. So we're pretty excited about this upgrade. This is being commissioned right now. As we speak, the commissioning team is trying to get this to work. And just to give you an idea of what the undulators look like, this is one undulator section. And there's about 33 of these on the hard X-ray line and 21 of these on the soft X-ray line. So like I said, not something you can put in your garage. Now, what does an FEL normally do? It doesn't do attosecond pulses. Attosecond pulses are an advanced capability. And it's a fruit of a lot of work from a lot of people. The FEL, granted, even the baseline mode of LCLS is a very complicated device. It's a fruit of a lot of the work of a lot of people. But what does it normally look like? You typically have pulses in the tens of femtosecond. That's if you just go to the control room, you ask the operators to do what LCLS normally does. You get pulses that look more or less like this. About 10 tens of femtosecond duration with peak powers in the tens of gigawatts. So at LCLS, we're lucky. We can actually measure the longitudinal phase space of the electron bunch for every shot. So what you see here is actually data. These aren't simulations. So this is what the time and energy distribution of our electron bunch looks like if the FEL is not working. Then you turn on the FEL and you see that these electrons are losing energy. And where is that energy going? It's going to the X-rays. And so now you can reconstruct by mapping the energy loss of these electrons, you can reconstruct your X-ray pulse duration. And that's like I said, that's what it looks like. Typically tens of gigawatts in tens of femtoseconds. But we've just discussed how interesting attosecond science is, and we want attosecond X-ray pulses to study molecules. So then how do you make attosecond pulses? This is a very idealized description of what happens. This is a figure I made in MATLAB. But you can imagine if you have an electron bunch that has a current distribution as a function of time that looks like this. You have some background, in the couple of kiloamp scale, and then you have a very short, very high current spike. And if you didn't know, if I hadn't told you how the FEL works, you would tell me, oh well, you have a lot of electrons here, so you probably make a short pulse here with a lot of background. But the FEL is an exponential instability, and so what happens is your high current spike here, it doesn't have a lot of electrons, but it has a lot of density. So the FEL is actually working much better there than it works anywhere else on your bunch. So by the time the FEL reaches saturation here on your very dense part of your bunch, it's still orders of magnitude lower anywhere else on your bunch, right? So this actually results in isolated attosecond pulses. So how do you do that in practice? Again, this is still at the idealized level. Well, you have your electron bunch that typically looks, well, we wish it looked like that, but you try to make it look like this, so somewhat flat distribution in time and energy. And what you do is you put a modulation in it. This is not that different from, for example, how a laser compressor works, right? You put a modulation on it, so there's a part of your electron bunch that has a negative chirp, right? So as you go through a dispersive device, you can stand up this distribution and make a part of the bunch that has like a high current spike. Then you send this to your undulator, and you have some hope of making short pulses. This sounds anticlimactic. I've told you how exciting everything is, and now I'm showing you a picture of my experiment being destroyed in New Mexico. If it feels anticlimactic, that's how it was in real life. This is a few years ago, as I was a Panofsky fellow. I was all excited to start this amazing program in attosecond science. And one day I drop off my kids. I open my email and I get this message that my Wiggler, the enabling piece of hardware for my entire science program, is sitting in the snow in New Mexico after being ejected from the back of a truck. So we spent a couple of hours with the engineers from SLAC, just staring at these photos. It doesn't look that bad. Maybe it's just the motors. Maybe we can. So then I get another email that a second truck had landed on it after the meeting. And next thing I know, I get a photo of my precious Wiggler sitting in a junkyard. And it's covered in eggshells and egg yolk, because it turns out the second truck was carrying eggs. This project was called XLEAP, X-ray laser enhanced attosecond pulses, and it was briefly renamed XLEAP. So anyway, I always show this. I like showing this to students because as a student, whenever something breaks in your lab, you might feel like it's the worst thing in the world, and it only happens to you. No, this happens all the time, and it can be a lot worse than something breaking in your lab. But we got our Wiggler back. It was sent back to Argonne. They rinsed it with water and got it back up and running. Okay, so we get our Wiggler back, and we start doing experiments. And so I told you, the way you make attosecond pulses is you take your electron bunches somewhat flat in phase space, right? Like I say, it's never exactly flat. But then, and then you try to make a modulation. There are several ways to do this. The first one we came up with was this thing called self-modulation, where essentially we extract infrared radiation from the tail of the electron bunch, and we use it to modulate the core of the bunch. So you get this modulation, and then with the dispersive section, you stand it up, and you end up with this stripe here. I won't bore you with the details, but when you see this large stripe, it means that there's a very high current spike there. So great, we have a high current spike, we send it into our undulator. And the first thing you do, for those of you who are not familiar with lasers and free electron lasers, first thing you do is always you look at the spectrum. The spectra are much easier to measure than pulses in the time domain. And this is promising already because the green line is what the spectrum from a short pulse would look like if we weren't doing any of this gymnastic, right? If you just go to the control room, you ask the operators, hey, give me a short pulse, you'll get something like this. Now we turn on our modulation and we get this much broader bandwidth. So you can already tell that this is working. It's doing something good. And remember, 2 eV is 1 femtosecond. So this is an 8 eV bandwidth. So there's some hope that these pulses will be shorter than a femtosecond. So the next thing you do, of course, as an FEL physicist, I saw these and I was already abundantly convinced that these pulses were short. But of course, you can't go to the community and say, hey, believe me, these pulses are short. You actually have to measure it. And that's a lot harder. The way you measure the pulse duration is through this thing called an autoclock, or angular streaking. What you do is you have a gas jet, and you extract electrons from the molecules in the gas with your X-rays. But you overlap a circularly polarized laser to your X-rays. And what that does, and then what you do is you measure the momentum distribution, the transverse momentum distribution of the electrons that come out of your gas jet. And now, if you don't have a laser here, these are 1s electrons. We're well above the absorption edge. So the distribution, the momentum distribution looks like these two lobes. So then what happens is you turn on your laser, and these electrons are born in the laser field. So they get kicked in the direction of the vector potential, not the direction of the field, the direction of the vector potential. So if the vector potential is pointing up at the time that your electrons are emitted, then these electrons will get kicked up. Then this is a circular polarized laser, so the vector potential is rotating as a function of time. So as it rotates, it kicks the electrons in whatever direction that vector potential is pointing at. Right? And that's why it's called an autoclock, because it correlates time with angle, just like an old-fashioned clock. And of course, so we did the experiment. This is easily one of the best days of my life. This is a really difficult experiment. Took about a year and a half and at least 2 or 3 attempts to make it work. But then we got it to work. And without doing any analysis, just by looking at this single shot data, you can already tell that these pulses are short because you can still see the two lobes. right? If these pulses were longer than the streaking wavelength, but longer than the time it takes for the laser to go around, then all you would see is just a smear. Right? Instead, you still see these two lobes, and so that tells you that these pulses are at least a lot shorter than the wavelength of the laser, which is 4 femtoseconds, 4.3 femtoseconds. Of course, you know, you don't just look at the data and say the pulse is short. We developed an algorithm that can take a single shot of this streaking data and turn it into a pulse profile. And we get, you know, what we thought we had just looking at the spectra. So this is data taken at 900 electron volts. You get an average pulse energy of 280 attoseconds. And at lower energy, this is around 600 dVs, you get a pulse duration, an average pulse duration of around 450 attoseconds. And I should say, this is a paper from 2020. We were the first. In the meantime, all the other major FELs in Europe, they've all joined the attosecond party. Fermi is a seeded FEL. They can make attosecond pulse trains just by combining harmonics, which is a lot of fun. PSI is also doing isolated pulses, and the European XFEL, we're hearing that they're doing it. They haven't published any paper. It's very recent. But what I'm saying is that this is actually a very interesting mode of operation for many, for other labs around the world. It's not just us that are working on this. Okay, so we have attosecond pulses. So what do we do with them? Well, you know, in FEL physics, just demonstrating a set of parameters does not automatically translate to experiments that can take advantage of it. So this was 4 years ago that we did this experiment, and we published a paper a couple of years ago. And since then, I would say 90% of my energy at work has been devoted to actually getting science out of these very short pulses. Of course, with the collaboration with James Cryan and all the people I've shown you in my first slide. So what are the questions we're asking ourselves? What specific questions we want to ask? Well, the first one is a very technical question. Can we observe coherent electron dynamics with site-specific X-ray observable? So at the beginning, we're not necessarily interested in answering a specific scientific question, but just can we actually do this? And then the follow-up question is, of course, can we turn that into something useful? And I've told you, right, solving the dynamics of electrons in molecules is impossible, I should say, in a self-consistent way, even with highly parallelized code. So my hope is that we can do enough experiments to provide an experimental basis for developing this kind of theory. And then, of course, the ultimate question here is, does this play any role on longer-term dynamics, so like on chemical dynamics? And spoiler alert, the answer to this is yes. We're getting there, and we don't know yet for the last one. But let me show you a couple of examples of experiments we did with these attosecond pulses. So the first one has to do with the Auger-Meitner decay. This is typically a fairly boring and well-known process in X-ray science. If you remove an electron from a core level, you create a core-excited state. One of the decay channels for this state is this Auger-Meitner process, which is driven by electron correlation. You can think of it as essentially other electrons in your atom or in your molecule colliding with each other. One electron gets pushed into the core hole, and the other one gets ejected. Right, so you start from a core-excited state, and you end up with a valence ionized state. And typically, we think of it as a fairly boring process. You know, it's just an exponential decay. But of course, you know, when you do things with attosecond pulses, things get a lot more interesting. So we set out to measure this process in the time domain with our short pulses, and we use the same auto clock that I've shown you before. Except now we're doing something a little more difficult. Instead of just looking at one photoelectron line, here we have 3. So this is a nitric oxide molecule, so you have nitrogen and oxygen, and we're tuning our X-rays at their oxygen resonance. Right, so we're creating neutral excited states in the molecule, core excited states. And of course, we're above the nitrogen K edge, so we're also creating photoelectrons from nitrogen. which is this line here. And then here you see the Auger-Meitner electrons coming from nitrogen and from oxygen. Now, the beauty of this experiment is that we actually have, a starting point for this whole interaction, which is the nitrogen for electrons. These electrons come out of the molecule at 100 eV roughly. So it means that, that they come out of the molecule almost instantaneously. Right? So we do not have synchronization between the laser and the X-ray. So for every shot, we have to determine at what time did the X-rays arrive. And luckily, we can do that just by looking at in which direction this photo line was streaked. This is a differential map, so it's streaked minus unstreaked. Wherever you see more red, that's the direction that these electrons were streaked, which is a measure of the arrival time of the X-rays with respect to your laser wavelength. Right? So this is our trigger. And then we look at a small wedge here of oxygen Auger-Meitner electrons. And then there's this beautiful animation from Taran that shows as a function of the streaking direction of the nitrogen electrons, which means as a function of the arrival time of the X-rays, how many electrons do I have here? And you see, of course, you see this fast decay, right? But it's not just a boring exponential decay. You actually see a little oscillation on top of this. And this is already a big step in the direction of can we measure electronic coherence with this stuff? Because this little ripple in your time dependence is actually caused by the fact that we're creating a superposition of excited states. There are 3 states in the in the resonant. Sorry, you can excite 3 different states at the oxygen resonance, and what you're seeing here is the beating of 2 of these states at a time. So this state can beat against this one or against this one. And if you do your math, this oscillation period corresponds to the 1 over the energy separation of these states. So this is still it's a pretty simple experiment. It doesn't really involve any complicated theory, but it is a proof of principle that says yes, these pulses are short enough and coherent enough that we can use them to study coherent excitations in electrons. Of course, this is a single pulse experiment. The problem, typically the ability to make an isolated short pulse doesn't necessarily mean that you can do time-resolved experiments with it. Typically, single pulse experiments are not very useful. It's a little bit like saying that you can understand, how people walk by looking at something like this, right? So normally, what you want to do is, with your short pulses, is do a pump probe experiment. So it's a situation where you create a sudden excitation and then you see how it evolves. So it's something maybe more similar to a 100-meter race, right? There's a time 0, right? And then you can study your process as a function in a time-dependent way. And how do you do that? You do it by making 2 pulses, right? A single pulse is not enough for that. The first pulse is called the pump, and it puts the sample in an excited state, and then you have a second pulse that comes with a control delay, and it probes your excitation as a function of time. You could be tempted to say, well, we have lasers at SLAC, there's plenty of lasers, let's just take a laser, put it in there, and time it with the X-rays. The problem, if you do that, is that the arrival time jitter of the X-rays with respect to a laser is at the femtosecond level, 10 to hundreds of femtosecond, right? So now, if you try to use your attosecond pulse with a laser that has 100 femtosecond jitter, your movie is going to look like this. Right? So not very helpful. So how do we fix this? We take the clue from the laser community. The way the laser community manages to make very precise pump probe experiments is by making 2 pulses using the same laser. That way there's no jitter because the source of both pulses is the same. And the idea is we have an undulator. It's pretty simple. We split it in 2 and we make 2 pulses, right? Now both pulses are coming from the same electron, so there's no jitter other than the jitter just coming from the noise in the electron beam. So the jitter between the 2 pulses that you're making is on the 100 attosecond level. And then you can you introduce a delay line for the electron, so you can control the delay between these two pulses. Again, we use our auto clock to measure this delay and make sure that we knew what we were doing. You can actually control the delay between pulses with 150 to 100 attosecond steps, depending on the energy. And again, this is work done by one of our graduate students. So, okay, we have 2 pulses, okay? And I've told you, you really want 2 pulses to understand time-dependent processes. So what we did next is, of course, we use this technique in a pump probe experiment. And again, this is the aminophenol molecule that you've seen over and over in this talk. We tune our pump below the carbon K edge. So this pump is now interacting only with valence electrons. It's below the energy it takes to excite any of the core excited states in the molecule. And what happens is that our pump has a lot of bandwidth, so it can create a superposition of 2 or more excited states, which means there are 2 or more valence electrons that can get ejected by this pump. And the key is that the bandwidth is large enough that this outgoing electron, there's some probability that the outgoing electron has the same energy, so you can actually observe interference. So what happens now, you've created this superposition of excited states, and you just let them go for a while. So now the charge, as I've told you, the charge starts moving around your molecule. And after a while, you say, okay, I want to see what's happening to my molecule. So you say, I want to see what's happening, say, at 2.7 femtoseconds. So what you do is you synchronize your probe. You send in your probe 2.7 femtoseconds later. And what happens is that now your probe is tuned to the oxygen K edge. So you can take an electron from the core and put it in either one of these valence holes that you've created. And the probability of a photon being absorbed at this energy is essentially a measure of the density of your hole, of the hole at the oxygen site. And so what you end up with is a core excited state, right? And this looks a lot like two-slit interference. So you have an initial state, you have a final state, and you have 2 or more ways to get there, right? So now you've created the conditions to observe interference. These 2 different pathways can interfere in your final measurement. I will not go over the excruciating details of how this absorption cross-section is measured. I will just show you the result. This is still a preliminary analysis. I'll confess this data, the analysis is largely correct. There is a 10 to 20% background we're still trying to identify. So I don't expect that the qualitative behavior of this will change significantly, but the exact numbers that you see plotted here might change by the time we publish the paper. But what's interesting is you actually see a very fast decay in the first femtosecond, and then a small revival a few femtoseconds later. And this is I should say, qualitative agreement with the theoretical calculations. These are done with a simulation code, using many nodes. You want to look at the red line, which is a pump bandwidth of less than 4 eV, which is the condition we had in the experiment. And you see something similar. You see a very fast decay and then a small revival later on. So again, this is still preliminary, but we're confident that we're actually observing the effect we're looking for, which is this very fast charge dynamics. And again, this is work done by a large group of students and postdocs. There are 4 Stanford graduate students that are leading this data analysis. So back to our scientific questions, right? We asked ourselves, can we use site-specific X-ray observables to observe coherent electron dynamics? The answer is yes, right? I've shown you these are two examples where we can make use of this large coherent bandwidth we're creating to induce and measure coherent dynamics, in coherent electron dynamics. And then the second question is, can we understand, more complicated things like coupled electronic and nuclear motion, electron correlation? Well, I think the answer to that question is we're getting there, right? We have one experiment. My hope is that over the years we'll be able to do many more of these experiments and provide the experimental basis for developing better models for molecular dynamics. So that's it for the science. I have just a couple more slides on what happens next. Most exciting thing is LCLS2. Now there's this new superconducting accelerator. It can fire X-ray pulses at up to 1 megahertz repetition rate. It's being commissioned as we speak. You can imagine attosecond science typically has to do with small signals, right? These coherent excitations, they're really exciting one electron. It's a superposition of states, but they all involve one electron at a time. So it's a small signal in a molecule that has many electrons. And typically your excitation fraction is, few percent to maybe 10%. So you're looking for small signals. So an upgrade to a megahertz repetition rate is very exciting in this context. I've shown you our data. We've taken only a handful of time steps. If we have a megahertz repetition rate, now we can really map the time evolution much more precisely. Can we do attosecond pulses with this new machine? Absolutely we can. This is Paris, France. This is part of Paris, France's PhD dissertation. We have a whole dedicated laser setup that allows us to do things like putting a little ripple on the electron bunch. This is a simulation. Put a little ripple on the electron bunch all the way at the beginning, and then let the collective instabilities in the beam amplify it, so you make this short spike that we know and love that allows us to do these attosecond pulses. Looking even further, everything I've shown you is based on conventional accelerator technology. The FEL aspect of it is absolutely not conventional. This is still very much an R&D, but it's all based on standard accelerator technology. There is a lot of work going on in the world at SLAC and everywhere else, well, it's at other places, on plasma-based accelerators. Plasma-based accelerators are exciting because they have accelerating fields on the order of gigavolts per meter. So that's about a factor 50 to 100 better than what we have now. And typically, the sell for this kind of technology is, well, accelerators are expensive, like this is a lot shorter, build your own. I was never excited about that. I work at SLAC, so availability of relativistic electrons is not a problem I have. But what makes me really excited is that you can use these really strong accelerating fields to make much brighter electron bunches that we have now. And I won't go into the detail, but essentially the shortest pulse you can make scales more or less like the square root of the brightness. 1 over the square root of the brightness. So if you tell me that you get 2 orders of magnitude better brightness, my first reaction is, well, I can get a factor of 10 shorter pulse. And what's interesting is this is essentially a new paradigm for soft X-ray sources, because we're not relying on the FEL instability anymore, this exponential growth that I've shown you. These bunches are so bright and the accelerating fields are so strong that you can essentially get out of the accelerator with 4 magnets. You can make an electron bunch that has a duration. The bunch itself has a duration that's comparable with the wavelength you're trying to make. So now you don't have to go through this long exponential process to amplify the microbunching. Your electron bunch already has a microbunching in it. And it's a single microbunch, which means now your pulse duration is essentially, it only depends on how many cycles you want to make in your undulator. So this allows us to do 2 things. First of all, make a lot of power. Right now, ask Paris how hard it is to make a terawatt pulse. It's really hard. This makes terawatts, I should say, almost for free. It's essentially what you get. But the really exciting aspect for me is that you can make pulses that are a few cycles long, which is something you couldn't dream of with a free-electron laser. A free-electron laser is inherently a narrow bandwidth process. So there's no obvious way to get to pulse durations of, say, tens of attosecond. This is a very forward-looking process. I don't anticipate that any of these will be using any of these for science in at least 10 years. But this is just to give you an idea of what's coming next. We're always looking for the next big thing. All right, and with this, I'm done. Just a short summary. We decided that attosecond electron dynamics are interesting and they're poorly understood. So what we did is we developed a technique to make attosecond pulses and, of course, diagnose them. And we use these attosecond pulses to induce and measure coherent dynamics in molecules. I've shown you this example with the measuring of the Auger-Meitner decay process and this still ongoing work on pump probe spectroscopy in aminophenol. And with that, I'd be happy to answer any questions.
Very nice intro, although I want to give you a chance to talk about some of the stuff that wasn't in your talk. So can you say something about when it might be possible to have attosecond, well-controlled attosecond pulses in the hard X-rays?
Oh, yes. Actually, That's the one thing that's easier to do at higher energies than lower energies is short pulses, because as I've shown you, this whole attosecond manipulation and the wiggler and all of that, you need to do that at soft X-rays because the bandwidth is narrow. But at free-electron laser, the way it works is that bandwidth increases like the square root of the photon energy, more or less. So at hard X-rays, you get attosecond pulses almost for free. All you have to do is find some way of messing up the electron bunches so that only a small part of it lasers. And you don't need to broaden the bandwidth. So actually, we had 8 eV bandwidth already in 2017. We never actually did a measurement of the pulse duration, but based on everything we know on FEL physics, those pulses should be around 200 attoseconds. So at hard X-rays, it can already be done. I should say the reason why we have not pushed very hard on that is because it's hard to make 2 of them. And as we've discussed, a single short pulse is not very helpful. You need 2 of them. And at hard X-rays, the gain length is longer. So if you split your undulator in 2, you get nothing. I think that's the sad truth. If we, I think we're already talking about LCLS-X, right? As a potential future upgrade of LCLS. I would say if we ever get there, we should probably build a hard X-ray line where you can do this. So now you can make 2, build an undulator that's long enough to make 2 pulses. So then we can. I should say TXI, you know very well, right? We're thinking of ways of sending both pulses from both undulators into the same experiment. That would potentially allow us to do attosecond pump, attosecond probe with the hard X-ray. So that was a long answer to your question.
So kind of a follow-up to Phil's question. There was a recent paper published by the Lucamel group that suggested that you could try and measure coherence and valence states with hard X-rays by looking at inelastic scattering if you used circular polarization with hard X-rays. So I'm curious, is there a way that you could also... It pains me to say that's you just need helical undulators, which it's not a difficult problem to solve. It's just a matter of funding. So eventually there will be delta undulators on our beamlines. It's as we work toward R&D priorities, we'll get there. Yeah. So I guess follow up on that. As a graduate student who's trying to figure out career trajectory, what's the time scale?
Ooh, just don't hold your breath. I would say if you're looking to graduate using that, maybe don't do that. It's about, I think we're looking at 2 or 3 years on the soft line. On the hard line will be longer than that. Yeah.
Great, thanks.
Yes. Could you do some of this or all of this in the frequency domain, but with other sources, or is it something that's really unique about pulses and time domain?
I think for very simple systems, like in NO, I've showed you all these really difficult experiments, and then I explained to you the result of the experiment, just showing you a spectrum. So for very simple systems, yes. But it's in the more complicated systems where you have, vibrational broadening, you have electron correlation. Then it's hard to disentangle all these effects just looking at spectra. And I think the time domain is what really gives you time domain, and the nonlinear experiment is what really gives you access to this richer information. Yeah.
I have a question. If you go back to one slide, I've seen this plot 3 times, but this is actually convenient because it's just here. I'm having a hard time understanding how you look at the oscillation with this periodic sort of.
Yeah.
So in other words, the thing shoots up again.
Yeah, it's because because we don't have what you're seeing is an average over many periods of the laser. The laser pulse is really long, right? So you're not sampling just one wavelength. You're sampling essentially continuously many wavelengths of the laser. So it's essentially you're like looking at a periodic repetition of this process. So the reason right?
It's periodic, but it's not 360 degrees. The period is not 360 degrees.
No, this is the period of the electronic oscillation.
Yes.
But then this larger period is just the period of the laser, right? If our laser wavelength was a lot longer, you would just see one of these, and then maybe down here it'll come back. Yeah.
Okay. Actually, I wanted to ask something else, which is entirely orthogonal to your theme here to make shorter pulses, which are also broader in
Yeah.
So what does it take? What's the best? So what if you want to have X-rays or even hard X-rays, a laser which is coherent?
Yeah. Oh, I should say.
Spatial coherent.
Yeah. So this, I should say, this is actually it's a factor 1.5 from the Fourier limit. So this is as coherent as an FEL gets. These are the most coherent pulses we can make compared to the Fourier limit. But I understand what you mean. What would it take to make a narrow bandwidth coherent pulse?
Narrow band,
Yeah. So maybe you should invite Jerome Wang next time. He's the leading this oscillator project. So the most straightforward way to do it is to seed the free electron laser. So start the instability with a coherent pulse and amplify it. That's clearly not an option at hard X-ray. So what you do is self-seeding, where you make a pulse, you put a monochromator in the middle of your undulator, and then feed it back to the electrons. So that gets you a little bit closer to the Fourier limit. It gets you, a coherence length of a few to maybe 10 femtoseconds. So it's never fully coherent, but it's a lot better than just starting from noise. There's this new project, which is this cavity-based FEL that I told you about in your office. You build an X-ray cavity around the undulator, and now you're bouncing the X-rays, around as they get amplified. And the reason that gives you a really narrow bandwidth is because, of course, at hard X-rays, these are a Bragg reflection, so the acceptance of the cavity is very narrow in frequency. So that gets you fully coherent pulses, also with a lot more power than you normally get, because it being stimulated emission, if you're starting the process from a lot of power, you're guaranteed to get more power at the end of it. So if you recirculate the power, you're essentially putting yourself in a situation where you can extract more energy from the electrons. But that's still, there's a test, which is still an R&D with only 2 passes that will happen next year. Or at least we'll start the experiments next year, and then this will really come to fruition once we have the next upgrade of LCLS2, which is the LCLS2 high energy, which I think it's the scale of 4 to 5 years. 5 to,
Is that near the damage? So are those mirrors easy to make?
Yeah, because the X-ray pulse is not that, it's not focused right inside the cavity, inside the undulator. The X-ray pulse is tens of microns in size. So it's not really going to burn, and damage is not the biggest concern, I should say. Yeah.
Okay.
Yeah.
One more question. Yes.
You talked about aerosolizable molecules as the sample you examined. Can you look at other things like thin films or solids?
In principle, yes. Yeah. I should say in solids, I know there's some push for doing experiments with solids. There's another whole R&D that I'm really excited about that I didn't have time to talk about, which is, so in solids, typically the interest is not in X-ray pump, X-ray probe, but pumping with, say, visible or terahertz, longer wavelength like. So we have this experiment where we actually use so as I said, if you try to do that with a laser, you fail because you have a lot of jitter. So we have an experiment where we want to use the field of the electron bunch itself. The electron bunch has a space charge field around it. It's just the sum of all the Coulomb fields of the electrons. And it's the same reasoning. That field is generated by the same electrons that make the X-rays. So you have attosecond stability. And so that's something that we actually have built infrastructure to do at least a demonstration experiment where we have this long wavelength field that's perfectly synchronized with the X-rays. All I can tell you is the concept works. We still, of course, working through the analysis. I'm happy to tell you more if you reach out to me. Yeah.
Okay, so thanks very much again.
Thank you. Thanks.
Allora, non andiamo dal